Quarter 2 Assessment Review. You can access this video and this review on srhschem.wikispaces.com or on YouTube channel LEFFELlabs. The first set of questions are about intermolecular forces. So the first question, what is meant by the phrase like dissolves like? So like dissolves like is a way to summarize how a solute and solvent will interact in order to form a solution. So a solute will best dissolve in a solvent that has a polarity similar to itself, and that polarity is due to chemical structure. So for example, anything charged, whether it's ionic or polar covalent, will only dissolve in polar solvents such as water. So if we look at a water molecule, the water molecule, due to uneven electron distributions, has a positive region that is electron poor on the hydrogen side, and on the oxygen side, it is electron rich, meaning it has a partial negative charge. So if we look at something like sugar or something like salt, both of these compounds are made of charges. Sugar is polar covalent, meaning that it also has those uneven distributions of electrons. So the positive regions on sugar can interact with the negative regions on water and vice versa, so that sugar will dissolve in water. If we look at salt, salt is made up of the sodium ion, which is positive, and the chloride anion, which is negative, and those can interact with the regions on water. Anything without a charge, so something that is nonpolar, is only going to dissolve in other nonpolar solvents, such as oil. So this hydrocarbon is oily, and it doesn't have any charged regions, so there's no way for it to interact with water, and a solution will not form. If I wanted to dissolve this, I would have to dissolve it in something else that was nonpolar. Next question is about intermolecular forces. So I have a molecule of H2S and a molecule of H2O. So first, let's identify the intermolecular forces in each molecule. Dispersion forces are attractive forces that occur in all covalent molecules. So it just has to be made up of nonmetals, in which case it will have dispersion. So dispersion forces happen whenever, even if there's an even distribution of electrons, for a split second they might not be evenly shared, and this can induce very temporary weak dipoles, but they still are attractive forces within a substance. The next strongest one is going to be dipole-dipole intermolecular forces. So this happens on polar covalent molecules because it's the result of a permanent dipole. So whereas dispersion is just a temporary transient dipole, dipole-dipole interaction is a permanent dipole, a permanently polar molecule. The strongest one is hydrogen bonding. So this is like a really, really extreme case of dipole-dipole interactions where the bond is so polar that we've given it a special name. And this type of bond will only occur if the molecule has a hydrogen bound to an F, an O, or an N. So the hydrogen of one molecule will attract to the F, O, or N of another molecule, causing a hydrogen bond. So if we look at H2S, it's going to have dispersion because it is covalent. We've got sulfur and hydrogen. And it's also going to be dipole-dipole. If I were to draw a line through the middle of the molecule, we see that the two halves are not symmetric. So because it's asymmetric, it's going to have a permanent dipole. In the case of water, water has all three of those intermolecular forces. It's got dispersion because it's made of hydrogen and oxygen. That's a covalent molecule. It also has dipole-dipole because just like H2S, H2O is not symmetric when we cut the molecule in half. It also has a hydrogen attached to an oxygen, so we also have hydrogen bonding. So what would happen is the hydrogen of water molecule A would be attracted to the oxygen of water molecule B. It's not really a chemical bond. It really would be better called a hydrogen attraction. So that one's got all three. So next, how is this useful? So the intermolecular forces will dictate the properties of a molecule of a substance. So the boiling point of water is really high. It's 100 degrees Celsius, whereas the boiling point of H2S is going to be negative 60 degrees Celsius. So what that means is that at room temperature, H2S is a gas, but water is a liquid. In fact, it's a liquid well above room temperature. So why do we have this difference in boiling point? So hydrogen bonding is occurring within water. So those attractive forces between water molecules are really strong. So if I want to turn that liquid into a gas by boiling it, I'm going to need a lot of heat to disrupt those very strong attractive forces. So this is going to cause water to have a much higher boiling point than H2S. Which molecule is more likely to have a strong odor? So again, this is dependent upon the strength of those attractive intermolecular forces. So the fewer intermolecular forces, the weaker the intermolecular forces, that means that those molecules can more easily escape each other. There is less attraction holding them together in one place. If it's easier to escape, that means that those molecules can more easily enter the gas phase, and they can more easily enter your nose so that you will have the strong odor. So if we look at these two molecules, the first one here is going to have only dispersion. It is covalent. Those are all nonmetals, hydrogen and carbon, but it is very symmetric, so it is nonpolar, and the hydrogens are all attached to carbon, so that bond isn't polar enough to allow hydrogen bonding. If we look at our other molecule here, this molecule has all three intermolecular forces. So it has dispersion because it's made of carbon, hydrogen, and oxygen, so it's a covalent molecule. And it has dipole-dipole because it is not symmetric. We also see there's a lot of pretty polar bonds going on in here. And it has a little hydroxide group, so it's got some hydrogen bonding going on as well. So that means that my first molecule can easily escape itself, and my second molecule cannot. So the first molecule is going to have a strong odor. The next set of questions are about naming and formula writing. So we have several names and formulas, and we need to fill out some information about them. So first I've got the sodium carbonate. So I need to identify what type of compound this is. Sodium is a metal, and carbonate is a polyatomic ion, so this is going to be an ionic formula. With ionic formulas, we have to first identify the ions. So sodium loses one electron, it has a +1 charge. And carbonate is CO3 minus 2. So now that we've determined the charges, we need to figure out how many of each ion is present so that the charges overall are neutral. So a quick way to do that, I can take that 2 and bring it down after the sodium. And I could bring that 1 down after the carbonate, but it's unnecessary to bring a 1 down. So this gives me 2 sodiums, each of which is +1. So a total positive charge of +2. So that will balance out the charge on the carbonate, which is -2. So my correct formula is Na2CO3. On my next formula, I've got P4O10. So this is going to be a covalent molecule because phosphorus and oxygen are both nonmetals. So this is a covalent bond. So whenever we name a covalent formula, we want to look at the number of each type of atom. So I've got phosphorus, and there's 4 of them. So the prefix for 4 is tetra. And then for oxygen, I've got 10 of them. So the prefix is deca. So I string that together, and I get tetraphosphorus decaoxide. So for phosphorus, decaoxide, the oxygen becomes oxide, and there's 10 of them. The next formula is obviously an acid because it has acid in its name. Whenever we name acids, the acids are named according to a certain set of stems. So the stem that matches this would be hydroblankic acid, and that corresponds to an ending of "ide." So that means that the phosphor was originally phosphide. So what's phosphide? Phosphide is just the ion form of phosphorus. So phosphorus is P, and it gains 3 electrons to get to an octet, so its charge is -3. I need to put a hydrogen in front because this is an acid, and the charge on hydrogen is always +1. So in order to make these charges neutral, just like with our ionic compound, I'm going to need 3 hydrogens. So that will give me +3, which will balance out the -3 from the phosphide. Next, I have FeSO4. So Fe is a metal, it's iron, and SO4 is a polyatomic ion. The fact that I have iron, sulfur, and oxygen, 3 different types of elements, is a big clue that there's a polyatomic ion in the formula. So this is ionic. Whenever we name an ionic compound, we have to name each ion. And if the metal is one where we don't know the charge, so if it is a transition metal, we have to indicate the charge with a Roman numeral. So I don't know the charge of iron just from looking at the table of elements. I do know the charge for sulfate, however. So sulfate has a charge of -2. There's only one sulfate, so the total negative charge is -2. And there's only one iron, so the charge on that one iron has to be +2. So whenever I name this, I'm going to call it iron 2 for the charge, sulfate. Next, I have perchloric acid. So this is also obviously an acid. So whenever I name this, I'm going to look at the stem. So this is a blank ic acid. There's no hydro. So blank ic acid corresponds to an ending of 8. So that perchlor was originally perchlorate, which is the polyatomic ion ClO4 with a -1 charge. It's an acid, so we start with hydrogen. Hydrogen has a +1 charge. So those charges are already balanced. The formula is HClO4. My next formula is H2CrO4. So 3 different elements. I know I have a polyatomic ion. And this one also starts with hydrogen, so I know it has to be an acid. So if I'm trying to find the name from a formula, I need to take a look at the anion, which in this case is going to be the CrO4, which is chromate. So that ends with 8. So whenever it ends with 8, we name the acid as a blank ic acid. So the chrome is going to go in that blank. So we have chromic acid. Next, I have cobalt-2 bromide. Cobalt-2 is a metal, and bromide is a nonmetal, so I've got an ionic compound. So I have to look at each ion. I've got cobalt-2 with a +2 charge, and bromide is the ion form of bromine, which has a charge of -1. So in order for these charges to balance out, I'm going to need 2 bromines for every 1 cobalt +2. So my formula is COBr2. Next, I have lithium, carbon, hydrogen, and oxygen. So 4 different elements are in this formula. So I know there's a polyatomic ion, therefore it is ionic. I've got the metal lithium. So whenever I name this, I'm just going to name each ion. So this is just lithium acetate. Lithium has a charge of +1 because it's in the first column on the table of elements. There is no need for a Roman numeral because we know the charge of the lithium. Acetate is the polyatomic ion C2H3O2, so we can just name it as acetate. So next I have copper 3 sulfate. So copper is a metal. Sulfate is a polyatomic ion. Therefore, this formula is ionic. And whenever I go to write this formula, again, use the name to figure out each ion. So this is copper with a +3 charge. And sulfate has a 2 charge. So it seems like these numbers aren't going to work out, but the common denominator there for 3 and 2 is going to be 6. So I should aim to have plus 6 and minus 6, and then my formula will be neutral. So if I bring that 2 down, that gives me 2 sulfurs. And then if I bring this 3 down, that's going to give me 3 sulfates. So 2 positive 3s makes plus 6, and 3 negative 2s make minus 6. So my charges are balanced. And I want to make sure that I use parentheses around the sulfate because I'm trying to say 3 sulfate ions, not SO43. My next formula, HCN, starts with hydrogen, so I know it's an acid. So I need to look at the thing that isn't hydrogen, and that would be the polyatomic ion cyanide. Whenever we name an acid that ends with "ide," we name it as hydroblankic acid. So cyan would go in the blank, hydrocyanic acid. Next, I have aluminum hydroxide. So aluminum is a metal, and hydroxide is a polyatomic ion. So this is an ionic formula. Aluminum will always have a charge of plus 3. Hydroxide has a charge of minus 1. Therefore, I'm going to need 3 hydroxides. And again, I need that parenthesis to indicate that there's 3 hydroxide ions, not OH3. Okay, next I have CuPO4. Copper is a metal. PO4 is a polyatomic ion. So whenever I name this, I need to indicate the charge of the copper because it is a transition metal. So I don't know the charge for copper, but I do know the charge for phosphate. I can look it up. It's minus 3. Copper is a metal. It's got to be a positive charge, and there's 3 of them. So the only way that works out is if each copper is plus 1. There's 3 of them, so that makes a total of plus 3, and that balances out the minus 3. So the name for this compound has to be copper 1 phosphate. Next, we have to determine if the formula is correct. So let's start with CaCl. This looks pretty good, but the charge for calcium is plus 2. So I actually need 2 chlorides to make this compound neutral. Next up, I have ammonium and nitrate. So I need to check the charges. I've got plus 1 for ammonium and minus 1 for nitrate. So this formula is already set. Now be careful, NH4 is 1 ammonium and NO3 is 1 nitrate. Treat it as a unit. Next I have H2CN. So the fact that I have 3 different elements here tells me right away there's a polyatomic ion, and that polyatomic ion is cyanide. So hydrogen is plus 1 and cyanide is minus 1. So I don't need 2 hydrogens, I only need 1. Next I have sodium, chromium, and oxygen. So there's a polyatomic ion in there, that's chromate. So sodium is plus 1 and chromate is minus 2. So this doesn't work. I need 1 more sodium, 2 sodiums for every chromate. So next I have CaOH2. So calcium is plus 2 and hydroxide is minus 1, but there's 2 of them, so that makes minus 2. So this formula is already good. Next I have barium, hydrogen, carbon, and oxygen. So there's definitely a polyatomic ion here. Hydrogen carbonate has a charge of minus 1 and barium is plus 2. So for this formula to work, I need 2 hydrogen carbonates. Next, we have to correct either the name or the formula. So I've got calcium and bromine. So calcium doesn't need a Roman numeral because it's always plus 2. Bromide is minus 1. So the name is correct for a compound of calcium and bromine, but the formula should be CaBr2. Next I have BaSO4, and we're calling that barium nitrate. I have SO4, which is not nitrate, that is sulfate. And barium, we know the charge of it from the table of elements. Roman numerals are unnecessary. FeCl2. So I know that chloride has a -1 charge, and there's two of them. So the negative charge is -2. There's only one iron, so its charge must be +2. So I shouldn't call this iron 3 chloride. I should call this iron 2 chloride. Then I have carbon disulfide. So if we look at the formula, there's one carbon, but we never start with mono. And then there's only one sulfide. So to fix this, I could either call it carbon monosulfide, or if I wanted to, I could also put a 2 after that sulfur. Potassium nitrate, so I've got K, which is potassium. I don't need a Roman numeral. NO2 is not nitrate, it's nitrite, one less oxygen. So this should be called potassium nitrite. Then I have H2SO4, and we're calling that hydrosulfuric acid. So SO4 is sulfate. It ends with 8, which means that we should name this just as an ic acid. So sulfuric acid would be the correct name for this formula. The next set of questions are about chemical reactions. So first, explain the law of conservation of mass, and how does a balanced chemical equation illustrate this principle? So during any chemical or physical change, the total mass before and after is always going to be the same. Matter is neither created nor destroyed. So this took a long time to figure out because there weren't instrumentation that were sensitive enough to detect that the mass had remained constant. And if you think about a lot of chemical reactions, like, for example, if one produces a gas, that could very easily escape and make it look like mass was not conserved. So how does a balanced chemical equation illustrate this principle? So whenever you balance a chemical equation, you are changing the moles of the reactants and the products. So the idea is you make the moles of each element equal on both sides of the arrow before and after the reaction. Next question, for each of the following formulas, X could be carbon, sodium, calcium, or nitrogen. Identify which element belongs with each formula. So let's start by looking at our nonmetals. We've got carbon and nitrogen as our nonmetals. So if I look at the electron configuration for carbon, I see that it's going to have 4 valence electrons. So nonmetals are going to bond based on how many valence electrons there are. So this carbon needs up to 4 bonds total in order to be stable, so it would have a full octet. For nitrogen, it's got 5 valence electrons, which means 3 of them are unpaired, so it can form 3 bonds. Now let's look at fluorine. All of the choices involve a bond with fluorine. So fluorine is a nonmetal. So when a nonmetal binds with a nonmetal, it's going to share an electron. So in this case, fluorine has 7 valence electrons. One of them is unpaired, so it needs to make 1 bond. It needs to share an electron with another element. So that means that carbon would need 4 fluorines to satisfy its 4 bonds, and nitrogen would need 3 fluorines to satisfy its bonds. So A has to be carbon, because that's the only one where 4 fluorines can combine, and B has to be nitrogen. So now let's go ahead and take a look at our metals, which are going to be calcium and sodium. So I can write out the electron configuration for calcium. And if we look, calcium has 2 valence electrons in the 4th energy level, but in the 3rd energy level, it's got a total of 8. So if calcium were to get rid of those 2 electrons, the highest energy level 3, would have a total of 2 and 6, makes 8 electrons. So that means calcium would form a +2 charge if it were to form a bond. Sodium has 1 electron in its 3rd energy level, so if it lost that 1 electron, the 2nd energy level has a full octet. So sodium's going to react by losing an electron, making its charge +1. When fluorine, which is a nonmetal, whenever it binds with a metal, it's going to gain electrons. So the metals are losing electrons, the nonmetal is gaining electrons. So in the case of fluorine, it has 7 valence electrons, which means that it needs to gain 1 more in order to have an octet. So the charge that fluorine would have would be -1. So calcium with its +2 charge would require 2 fluorines, whereas sodium would require 1 fluorine because its charge is +1. So that means that XF2 has to be calcium and XF has to be sodium. As far as types of chemical reactions, so first we have a combination reaction. This occurs when 2 or more reactants combine together to make one product. The opposite of that would be a decomposition reaction, where a single reactant breaks down into 2 or more simpler products. Next, the description says a lone element replaces a less reactive element in a compound. So this is going to be single replacement because we're talking about a lone element. So the way that this is written, the lone element is A and it replaces B in the compound. That will happen if and only if A is more reactive than B. So we would need to use an activity series to determine that. Double replacement is kind of like single replacement, except instead of a single element, we have 2 ionic compounds that switch spots. So if I have A and B reacting with C and D, A and C are going to switch places. This usually occurs in an aqueous solution, and it's going to be driven by the fact that one of the products is not aqueous. So it has to form something that isn't aqueous. Otherwise, those ions just all float around in the water and nothing happens. The last one, I've got a carbohydrate reacting with oxygen to form carbon dioxide and water. So this is a combustion reaction. For the hydrocarbon, it's CXHYOZ. X, Y, and Z can be any number, including 0. So you could have something like a hydrocarbon like methane, where there's no oxygen, but there's 1 carbon and 4 hydrogens. Any combination there will work. So now we have to balance some chemical equations, which means we also need to write some chemical equations. So the first one, calcium reacts with iron 3 chloride, predict the products. So first, we know that calcium is going to be Ca, and it's going to react with iron 3 chloride. So the 3 tells me the charge of iron is +3, and the charge on the chloride is -1. So I've got to have 3 chlorides in order for this compound to be neutrally charged. So let's look at what the products are going to be. I've got a lone element and a ionic compound. So this is a single replacement reaction. That lone element, that lone calcium, is going to replace an element in a compound only if calcium is more reactive than iron, which it is. So I identified that the charge on calcium is +2, meaning that it would form a cation, so it's going to replace a cation, in this case iron. So instead of iron chloride, I'm going to get calcium chloride. Calcium is +2, chloride is -1, so I need 2 chlorides. And now by itself is going to be iron. So now that I've got my equation, my skeleton written out, we can go ahead and balance this. I've got calcium, iron, and chlorine. 1 calcium, 1 iron, 3 chlorines. On the other side, 1 calcium, 1 iron, and 2 chlorines. So first thing we're going to look at is the chlorine. So I've got 3 and 2. So the common denominator there is going to be 6. So I want to aim to have 6 chlorines on each side. So if I put a 3 in front of calcium chloride, that's going to give me 6 chlorides, but it also gives me 3 calciums. Okay, so now we can go to our other side and put a 2 in front of the FeCl3. That'll give me 6 chlorines, like on the product side, and 2 irons. So now I just need to go back and fix calcium and iron. put a 3 in front of calcium, and put a 2 in front of iron, and now we're balanced. Next, I have FeCl3 plus NaOH makes FeOH3 and NaCl. So I've got iron, chlorine, sodium, and then I have hydroxide on both sides of the arrow. So rather than splitting that up into hydrogen and oxygen, I'm just going to keep it together as hydroxide because it appears on both sides of the arrow. So we can go ahead and count. So we can start with the chlorine. So I'm going to put a 3 in front of NaCl. So that gives me 3 chlorines, but it also gives me 3 sodiums. So now I can go to the opposite side, and if I put a 3 in front of sodium hydroxide, that's going to fix up my balancing. So I have 3 sodiums on each side and 3 hydroxides on each side. So now my equation is balanced. This is a double replacement reaction because the cations, the iron and the sodium, switch places. So now sodium phosphate and calcium chloride react to form calcium phosphate and sodium chloride. So sodium phosphate, sodium is a +1 charge, and phosphate is a -3 charge. So I need 3 sodiums for every 1 phosphate. That's going to react with calcium chloride. So 2 chlorines for each calcium because calcium is a +2. And I'm going to form calcium phosphate. So in calcium phosphate, I need 3 calciums to make +6 and 2 phosphates to make -3. Or 2 phosphates to make -6 so that my charges are balanced. We have to include a parenthesis around the phosphate so that I know it's 2 phosphates, not PO42. And sodium chloride. That's easy because it's +1 and -1. So here's my skeleton. We can go ahead and take inventory. I've got sodium phosphate on both sides, calcium and chlorine. So we can count. There's 1 phosphate on the reactant side and 2 on the product side. So we can pick any of these to start with. Why don't we start with calcium chloride? So I put a 3 in front, and that gives me 3 calciums, but it also changes the number of chlorides to 6. So next I'm going to work on my sodium here and fix my phosphate as well. So if I put a 2 there, that's going to give me 6 sodiums and 2 phosphates. So now the only thing that's not balanced is the Na and the Cl, which is convenient because if I put a 6 on the other side, I end up with 6 and 6, so it's balanced. This is also a double replacement reaction. The cations, which are sodium and calcium, are going to switch spots. Methane gas is burned in the presence of oxygen gas. So methane is CH4, and it's going to burn in the presence of oxygen gas. We have to predict the products. So this is going to be a combustion reaction where a hydrocarbon reacts with oxygen, and we're going to form carbon dioxide gas and water vapor. So here's my skeleton equation. Let's take inventory. I've got 1, 2, and 4 on my reactant side. So 1 carbon, 4 hydrogens, and 2 oxygens. On my product side, 1 carbon, 2 hydrogens, and 3 oxygens. Be careful, oxygen is in 2 places. It's with carbon dioxide and it's with water. So we have to make sure we count both places each time we change a coefficient. So I'm going to start by fixing my hydrogen. If I put a 2 in front of H2O, that's going to give me 4 hydrogens, so now that's balanced. And now I've got 2 oxygens with water, plus the 2 from carbon dioxide, so now I have 4 oxygens. So to resolve that, I just put a 2 in front of the O2, and that gives me 4 on each side. Next question asks us to construct an activity series based on some experimental data. So we took metals A, B, C, and D, and reacted them with the nitrate salt of each metal in an aqueous solution to see if they reacted. So, if we look at B has a total of 3 reactions, meaning that it will replace A, C, and D in single replacement reactions. A will only replace C and D can only replace C. C is not reactive enough to place anything. So this gives us our order. B is most reactive and C is least reactive. So we use an activity series in order to predict whether or not a given reaction will happen. So in order for the reaction above to occur, the lone element, which we're representing with a question mark, has to be something that is more reactive than element D in the compound. So anything that is more reactive than D is going to work. So it could be A or it could be B. Both of those would give us a reaction. Next set of questions are mole calculations. So explain what Avogadro's number is and what do we use it for? So Avogadro's number is a way to count the number of atoms. So one mole is going to be equal to 6.02 times 10 to the 23rd atoms. So this is how many things are in a mole. It allows us to count by groups. So for example, we might count eggs by the dozen instead of by the individual egg. In the case of Avogadro's number, we're counting atoms, which are really, really small. So I need a really big number to count them by. I can't count them by dozens because a dozen is just not enough. So instead we count them by the mole. So how many moles are in a 35-gram sample of sodium chloride? So this is where we can use our mole roadmap. The mole roadmap allows us to convert between different units. So for example, I can take our 35 grams of sodium chloride and change it into moles. So to go from grams to moles, I use molar mass to do that. So I'm going to start with my 35 grams of sodium chloride. And in order to convert it into moles, I need molar mass. So I find molar mass by adding up the number of atoms in the formula and then multiplying each one by the atomic mass. So for sodium and chlorine, there's one of each, and the molar masses come from the table of elements. So that gives me the molar mass of this compound and allows me to convert from grams into moles by dividing by the molar mass. Next, how many molecules are present in 15 liters of carbon dioxide? So I'm starting here with 15 liters, and I want to get to molecules, which are particles. So I need to change liters of gas into moles, and then moles into particles. So I accomplish that. I take my 15 liters of carbon dioxide gas, divide by the molar volume. So 1 mole of a gas takes up 22.4 liters of volume. Next, I need to convert moles into molecules, so I'm going to need to use Avogadro's number. So there are 6.02 times 10 to the 23rd molecules in 1 mole. Next, how many grams are in 2 moles of sodium atoms? So I'm starting with mole, and I want to get to grams. So I'm going to need to use molar mass to do that. So 2 moles of sodium, I take the molar mass of sodium, and I'm going to multiply in order to get the mass of 2 moles. So basically I'm just doubling the molar mass. How many grams are present in 1.204 times 10 to the 24th atoms of iron? So I'm starting over here with representative particles, and I want to get to mass in grams. So I need to convert particles into moles and then moles into mass. So I start with Avogadro's number to convert atoms into moles, And then I use molar mass in order to convert moles into grams. So I have more than a mole. A mole would be times 10 to the 23rd, so this is more than a mole. So I expect to have more than 55.84 grams, because that's the mass of 1 mole. Explain why a mole of silver and a mole of gold will have the same number of atoms, but different molar masses. So a mole is 6.02 times 10 to the 23rd atoms, and that's always going to be that number. So a mole of gold will weigh more than a mole of silver, even though they both have the same number of atoms, because a gold atom is heavier than a silver atom. So if you had 25 sumo wrestlers and then 25 preschoolers, it's the same number of people, but the mass of a preschooler is much smaller than the mass of a sumo wrestler. So the mole of gold is like our sumo wrestler, and the silver is like our preschoolers. Which has a greater percent by mass of oxygen, so potassium permanganate or water? So to find the percent composition of an element, you need to take the molar mass of that element and divide it by the molar mass of the compound, and that will be multiplied by 100% to give us percent. So KMnO4 has a molar mass of 158 grams per mole, and oxygen, I take the molar mass of oxygen times 4, and I get 63.996 grams per mole. So this will give me a percentage of 40.49% oxygen. We can do the same thing with water. The molar mass for water is 18. The molar mass for oxygen is just under 16. So that means that water is 88% oxygen. So the one that has a greater percent by mass would be water. Next are some stoichiometry problems. So here's the Haber process. This is a necessary reaction for making ammonia that is used in fertilizer. So how many moles of nitrogen are needed to make 24 liters of ammonia? So I'm going to start with my given, which is 24 moles of ammonia over 1. And I want to get to moles of nitrogen. So my first step is to take whatever I'm given and change it into moles. We're already there, so my next step is a mole ratio. So I'm done after that because this problem just asks for moles of nitrogen. So mole on top of mole means mole ratio. That comes from our balanced equation. So in my balanced equation, I have 1 mole of nitrogen and 2 moles of ammonia. So I'm going to get 12 moles of nitrogen in order to make 24 moles of ammonia. What is the limiting reactant when 10 moles of nitrogen react with 12 moles of hydrogen? So I have 2 givens here. I'm starting with moles. So my next step is a mole ratio. And we want to pick a product. There's only one, so we're going to pick ammonia. So this will let me calculate moles of ammonia. I can do the exact same calculation starting with 12 moles of hydrogen. I'm going to have a different mole ratio here, but that gives me 8 moles of ammonia. So what these 2 calculations have told us, if I started with 10 moles of nitrogen and I had plenty of hydrogen, I would make 20 moles of ammonia. If I started with 12 moles of hydrogen and had plenty of nitrogen, the most ammonia I could make would be 8 moles. So whenever I mix these 2 together, the most I can make is going to be 8 moles, and the hydrogen is my limiting reactant. Next, we have an equation, and it says what is the limiting reactant when 20 grams of sodium hydroxide react with 22.5 grams of H2SO4. So don't be fooled into thinking just because one number is bigger than the other that that's automatically going to be the excess reactant. We have to look at a mole relationship in order to figure that out. So we've got an unbalanced equation. So our first task is going to be to balance that. I've got the polyatomic ion sulfate on both sides, and I also have the polyatomic ion hydroxide on both sides, but it's hiding. So I can count. Whenever I get to count the hydroxide on the other side, I'm going to take that H2O and instead write it as HOH. Now I can see there's one hydrogen and one hydroxide hidden in that water formula. So we can start by balancing sodium. 2 sodiums and 2 hydroxides. And then if I go to my other side and put a 2 in front of the HOH, that gives me 2 hydroxides and 2 hydrogens. So now that's balanced. So, determine the limiting reactant. I've got 2 givens, so I'm going to do 2 calculations. First, I need to convert grams of sodium hydroxide into moles. That's always your first step, to take your given and change it into moles. Next step is going to be a mole ratio. So I'm going to take my moles of sodium hydroxide and change it into moles of a product. So as far as which product we want to pick, we have 2 choices. We're going to pick the sodium sulfate because the next problem asks us specifically about sodium sulfate. So it makes sense to calculate that one. You could pick water and still figure out the limiting reactant, but then you would have to do another set of calculations to figure out how much sodium sulfate would be made in the next set of problem. The next problem also asks us to give us the sodium sulfate in grams, so we might as well convert moles into grams. So this will give me grams of sodium sulfate. Grams in moles means molar mass for sodium hydroxide. Moles on moles means mole ratio from the balanced equation. And then I have grams and moles again, this time for the sodium sulfate. So that would make 35.5 grams of sodium sulfate. So now I'm going to repeat basically the exact same calculation, but this time I'm going to start with the 22.5 grams of H2SO4, convert that into moles, do a mole ratio. I want to make sure that I pick the same product because I'm going to compare my answers at the end, and they need to be in the same units in order for that comparison to work. So we can take moles into grams. So grams and moles is going to mean molar mass. Moles on moles is a mole ratio from the balanced equation. Grams and moles again of sodium sulfate. I can make 32.6 grams of sodium sulfate. So that means that the 22.5 grams of H2SO4 are actually my limiting reactant because it makes less product. What is the theoretical yield in grams of sodium sulfate? So because we were smart with how we were solving that last problem, we've already found this. I can make 32.6 grams, and then I'm going to run out of that limiting reactant. So it's important to know the limiting reactant in a reaction because it determines how much product I can make during the course of the reaction. So it might be that I'm aiming for a specific amount. It might be that maybe one of my reactants is expensive, so I want to make sure whenever I do the reaction that I don't waste any and that I use it all to make product. A student performed the reaction and obtained 29.60 grams of sodium sulfate. What is the percent yield? So to find the percent yield, we need to take the actual yield or the experimental yield and divide it by the theoretical yield, which comes from calculations. So I can plug in these numbers, multiply it by 100%, and they got a percent yield of 82.6%. The next set of questions are about molarity. A solution is made with 150 grams of sodium chloride in 800 milliliters of water. Calculate the molarity. So molarity is going to be moles of solute over liters of solvent. So I need to take the 150 grams of sodium chloride and convert that into moles. So 150 grams over 1. Want to convert grams into moles, which means that I need the molar mass. So I have 2.57 moles. Next, I want to convert the 800 milliliters into liters. So to do that, we just divide by 1,000 milliliters to get 0.8 liters. Plug those two numbers into my molarity equation, and that gives me my molarity, 3.21 molarity, or molar, or you could say moles over liters. How many moles of hydrochloric acid are present in a 10 milliliter sample of 6 molar hydrochloric acid? So in this case, I'm solving for moles, and I'm given the molarity and the volume. So let's first start by converting that 10 milliliters into liters by dividing by 1,000. Then I'm going to plug in backwards and solve for moles. So I have 6 molar is equal to X moles divided by 0.01 liters. So I multiply both sides by the denominator, so it cancels out, and that leaves me with X is equal to 0.06 moles of hydrochloric acid.